Okay, these little bright drops you see right here are little oil droplets, and I see one that's slowly falling. So let's say there's a couple of reference lines. I've already started the stopwatch ideally, and tick, 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 time is running. We're going to just continue timing it until it gets to this second reference line. So let's see if this oil droplet gets past my hand right here. Timing it, timing it, timing it, and then we stop. We let it keep falling to give us a little bit of time. So I'm no longer timing it, but I'll let it fall past this reference level. Now we turn on an electric field and we should see it rise. And then start. We begin timing it, and then it's going to get to the second reference line. And when it passes the second reference line, again, we'll stop timing it. So we stop and let it keep rising for a little bit, give us a moment to record our measurement. Then we turn off the electric field, and under the influence of gravity, the oil droplet starts to fall once again. So we start timing, tick, 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 and we're going to keep going until it gets to this reference line. And we'll do that over and over, watching the oil drop fall under the combined force of gravity and air resistance at a terminal velocity. We switch on electric field. Now there's three forces acting. Electrostatic force up, gravity down, and then air resistance then acts in the downward direction while it's rising. Under the combination of those three forces, it's a different terminal velocity. So by studying the rise and fall, we can get the terminal velocity while falling and the terminal velocity while rising. Ultimately, from that, if we get data for enough of these little oil droplets, believe it or not, we can use that to verify the fundamental charge, the charge of an electron. So we're going to turn on the lights, and I'll show you exactly how we're getting this image on the screen. So this was the camera that was projecting onto the screen, thanks to this camera that's looking into this microscope that allows us to see little oil droplets that are sitting here in that little space between these two copper plates. So this is a circular parallel plate capacitor, and the electric field between those plates when they're charged up should be uniform. Now the two plates are separated by 7.6 millimeters. This is the little separator that creates the space between those. Now, electric field can be measured in newtons per coulomb and also in volts per meter. So this power supply that's charging the plates is set to 500 volts. And if that 500 volts is applied across a spacing of 7.6 millimeters, you can do the math to figure out the strength of that electric field. So this is the little squirter for the oil droplets. And when we put this back together, those oil droplets can be injected into here, and they'll fall. And it's just a very few of them make it through that tiny little hole and then into the space between the plates, okay? So that's essentially the whole setup to this Millikan's oil drop apparatus. Obviously, we wouldn't normally use a camera. You would be here with your eyes peering into the microscope with a stopwatch in your hand. And this is the switch that turns on and off the voltage to those plates. So with the switch in this middle position, there's no electric field, and the oil droplets just fall under the combined influence of gravity that way and air resistance this way. When we turn the switch either way, this is just top plate is positive, this is top plate is negative, so we can make the electric field lines either point down or point up. And there you have it.